Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 6 on rectangles. So now that we've kind of laid our groundwork with parallelograms, we're going to start to explore special types of parallelograms, right? Those are the rectangles, the rhombuses, and the squares. We're going to take each one of them a lesson at a time. So let's jump right in and take a look at the humble rectangle. Now, rectangles, we now begin to explore the three special types of parallelograms. As I mentioned, the rectangle, the rhombus, and the square. We begin this lesson with the rectangle. So let's make sure that we understand yet again what the definition of a rectangle is for our particular purposes. A rectangle is any quadrilateral that contains only right angles, or alternatively contains exactly 4 right angles. Now, all rectangles are also parallelograms, which we will prove in the first exercise. And we want to prove that, right? Because once we know that rectangles are also parallelograms, then everything that's true about parallelograms, the 4 major properties of parallelograms, will also be true of rectangles. So let's take a look in exercise number 1 at how we prove that a rectangle is a parallelogram. Lines M, N, S, and T create rectangle ABCD as shown. Give an explanation for why line M and line N must be parallel, and why line S and line T must be parallel, thus showing ABCD is a parallelogram. All right, well, there are tons of different ways to do this, but keep in mind, right, at the end of the day, what a parallelogram is a quadrilateral that has 2 pairs of parallel sides. So what we want to think about is, okay, if I've got, 2 lines here and 2 lines here that intersect such that these 4 angles are all right angles, how can I claim that line M is parallel to line N and line S is parallel to line T? What I'd like you to do is pause the video now and consider that question. All right, well, there's tons of different ways, including, right, like the 2 major ways that we've shown that lines are parallel in the past, right? One way is by showing that alternate interior angles are congruent. Well, keep in mind that when 2 lines are perpendicular, every angle that they form when they intersect is a right angle. So if that's a right angle, this is a right angle, right? And this is a right angle, and this is a right angle, and this is a right angle, right? Those are all right angles. But of course, if these 2 angles are right angles, they're congruent to each other, which is an alternate interior angle pair, which means line M is parallel to line N, right? We could also use the idea that we've got congruent corresponding angles, right? And we can do that because this angle up here is congruent to that angle down there, and they're corresponding angles. Likewise, this angle and that angle over here are corresponding angles, and they're congruent because they're right angles. So there's lots of different ways to do it. One way I'd like to introduce, though, that we haven't seen in the past is a little bit different, which is when 2 angles are same side interior angles and they're supplementary to each other, 2 lines are parallel. So if 2 same side interior angles are supplementary, then lines forming them are parallel. And that one really just follows from the alternate interior angles being congruent, make lines parallel. Then we can go with the same side interior angles being supplementary, also make the lines parallel. This was actually the main way that Euclid proved that lines were parallel. If 2 angles that were on the same side of a transversal were supplementary, then the 2 lines forming them would have to be parallel. And of course, 2 90-degree angles are supplements of each other. So because these 2 angles are supplements, M and N have to be parallel. And because these 2 angles are supplements, or these 2 angles are supplements, S and T have to be parallel, right? So I'm going to say since all right angles are supplementary, that looks like an H, are supplementary to each other, lines M and N are parallel, and lines S and T are parallel. And again, you could use that reasoning, you could use the alternate interior angle reasoning, you could use the corresponding angle reasoning, so many different things. But again, the major takeaway from this is really extremely important, which is now that we have proven or justified that a rectangle must be a parallelogram, every property of parallelograms rectangles now have. Now think about that. One property of parallelograms is that opposite angles are congruent. Well, that's pretty much a given. Another property is that adjacent angles are supplementary. Again, that's sort of true regardless on rectangles. But some things that wouldn't necessarily be immediately obvious is opposite sides are congruent, right? That is a property that directly comes from a rectangle being a parallelogram. The other piece, the diagonals, will bisect each other. That is also a piece that is very specific to parallelograms, but now is a property of rectangles because all rectangles are parallelograms. All right, let's keep going and take a look at other things about rectangles. Now, the diagonals of rectangles. Since rectangles are parallelograms whose four angles are congruent, their diagonals take on a special property, okay? There's something special about the diagonals of rectangles that isn't generally true about the diagonals of parallelograms. And let's take a look at that in exercise number 2. Given rectangle MNPQ shown below, do the following. Letter A, use a ruler to compare the lengths of the two diagonals. Round to the nearest tenth of a centimeter. So what I'd like you to do is just take your ruler, right? I'd like you to measure the length of MN, the length of NQ, and compare those two. Pause the video for a moment right now. All right, well, let's take a look. Right? If I bring my ruler up and take a look at this, then what I'm going to end up having is, for some reason, this is in inches. Let me switch it to centimeters. I'm going to get 6.4 centimeters, right? And if I do it down here and I measure that, that is also 6.4 centimeters. So what can I see? The lengths of the two diagonals of this particular rectangle, at least, are the same length, okay? And that is true of every rectangle. Now again, it probably seems immediately obvious. Oh, of course the lengths of the two diagonals are congruent. But that is generally not true of parallelograms. In most parallelograms, you have a longer diagonal and you have a shorter diagonal. Granted, the diagonals bisect each other, but one of them tends to be longer than the other. All right, but not in a rectangle. In a rectangle, the two diagonals will always be congruent. So let's actually prove that in part B. All right, actually let me get this thing out of here so that we don't have to worry about it. All right, so in letter B, I want to prove that MP is congruent to NQ. All right, so what I'd like you to do is pause for a moment. And again, keep in mind, the one given that you know at this point is that MNPQ is a rectangle. Pause the video and see how you can think about why MP and NQ must be congruent. Take a moment. All right, well, let's take a look at what we know, right? At this point, what I know, since it's a rectangle, is I obviously know that that angle and that angle are right angles. All right, great, right? I also know that the other two vertex angles of the rectangle are right angles, but I'm just going to work with those two. Now I also know that a rectangle is a parallelogram, and because a rectangle is a parallelogram, I know that sides that are opposite are congruent. So I could say that those two sides are congruent. I could also say that MN is congruent to QP, but I'm just going to leave it like this right now. Now finally, I also know, obviously, that QP is congruent to itself. Why does that matter? Well, if I take a look, let me go with a highlighter here really quick. Okay, if I highlight this particular triangle, right, and let me kind of bring it out real quick, and let's highlight another one, but let's go with it in yellow. If I highlight this triangle, and let's put that away, right, what I have just done at this point is I have now marked up my diagram like this, right? And this being MQP, and this being NPQ. So it looks like I can prove that this triangle and this triangle are congruent by the side angle side triangle congruence theorem. And once I know that this triangle is congruent to this triangle by side angle side, I can then say that MP is congruent to NQ by my friend CPCTC, right? I think we've probably used that principle in geometry more than any other one. So let's try to get it down. I'm going to write this in a paragraph style. So let's begin here, all right? Because MNPQ is a rectangle, I'm going to say that angle MQP is congruent to angle NPQ because they are both right angles. They are both right angles. Right? Then I'm going to say something like this. I'm going to say because MNPQ, give me a little more space, is a rectangle, it is also a parallelogram, and thus, what do I know? MQ is congruent to NP, right? Opposite sides of a parallelogram are congruent. So right now, right, I've got an angle equal to an angle, a side congruent to a side. Finally, QP is congruent to itself. So triangle MQP is congruent to triangle NPQ by side angle side. This leads to, to true MP being congruent to NQ by CPCTC. Oh my, just barely fit. Let me kind of move it up a little bit there so we can still see the picture. Again, let me walk you through it one more time, all right? And the order here is not absolutely essential except for the last little part. You know, because MNPQ is a rectangle, angle MQP is congruent to angle NPQ, right? Those are this angle and this angle because they are both right angles. Because MNPQ is a rectangle, it's also a parallelogram, which we proved in exercise 1, and thus MQ is congruent to NP, right? Opposite sides of a parallelogram are congruent. Finally, QP is congruent to itself, right? That's the whole reflexive property. So triangle MQP is congruent to triangle NPQ by the side angle side theorem. This then leads to MP is congruent to NQ by CPCTC, right? And again, it's remarkable. Most parallelograms, right? This angle and this angle aren't congruent. So you can't actually conclude that this triangle and this triangle are congruent in a general parallelogram, right? And that's why in general in a parallelogram the diagonals aren't the same length. But in a rectangle, because all the angles are equal, and they all happen to be equal 90 degrees, but that's not so much relevant here. Because these two angles are congruent, that means we can conclude that those two triangles are congruent, and therefore those two lengths or those two segments are also congruent. It's kind of cool. All right, pause the video now, write down any of this scratched out proof that you need to. All right, let's keep going. Oh, there it is. Like, where'd that go? All right, here we go. Exercise number 3. In rectangle RSTU, it's known that RS is 12 and ST is 5. What is the length of diagonal SU? All right, so here we finally have a problem that's not a proof, right? It's just a straight up like, let's see what's going on here. So what I'd like you to do is pause the video for a moment, draw a good picture, and see if you can use something that we've learned previously in this course to figure out the length of diagonal SU. All right, well, let's do it. Really great to have good pictures. This should be pretty easy. Here we go. RSTU, right? We know that RS is 12, ST is 5. Again, because this is a parallelogram as well as a rectangle, we can also say that's 5 and this is 12. We want to know the length of diagonal SU. So I draw that in. I put in my right angle like that. And of course, anytime I have two sides of a right triangle, I can always find the length of the third side by using the Pythagorean theorem. So if I would call the length of the diagonal C, I can say 5 squared plus 12 squared is equal to C squared. 25 plus 144 is equal to C squared. 169 is equal to C squared. Take the square root of both sides, and C is equal to 13. It is very often the case, that we will have a situation where when we are working with a rectangle or a square, which we'll see in a few lessons from now, we sometimes will have to do the Pythagorean theorem, all right? Right triangles can naturally be formed by drawing in the diagonals of the rectangle, and therefore the Pythagorean theorem comes into play. Not always, but sometimes. All right. Now, just like with parallelograms, there are conditions that are sufficient or enough to prove that a figure is a rectangle without showing that it's got 4 right angles. All right, so let's take a look at the sufficient condition set number 1 for rectangles. If a quadrilateral is a parallelogram, and that parallelogram has congruent diagonals, then it is a rectangle. So this is cool. Now, watch out, right? This is similar to the fact that all rectangles have congruent diagonals, but this is saying, look, if I've got a parallelogram and I know that its diagonals are the same length, then that parallelogram has to be a rectangle. Now, it's important. It's got to be a parallelogram. You can easily have a quadrilateral that has 2 congruent diagonals that is not a rectangle. Let me say that again. You can have a quadrilateral, a 4-sided figure that's got congruent diagonals that is not a rectangle. And we'll see one a few lessons from now when we look at what's known as an isosceles trapezoid, which has got 2 congruent diagonals but isn't a rectangle. But as long as it's a parallelogram and has congruent diagonals, then it's got to be a rectangle. So let's justify sufficient condition set number 1 in exercise number 4. In the diagram below, all we are given is that ABCD is a parallelogram whose diagonals BD and AC are congruent. Explain why triangle ADC must be congruent to triangle BCD. All right, great. So again, I know it looks like a rectangle. That's because I'm trying to prove it's a rectangle. But right now, let's say all you know is that ABCD is a parallelogram and that AC and BD are congruent. How can I justify, and let's highlight these things again, I think it's really helpful to have them highlighted. How can I justify that ADC is congruent to that. Oh, I did get it. Nice. I want to justify that those two triangles are congruent. Pause the video now and think about this a little bit and only use information that you know at this point. All right. Well, let me go back to the pen real quick. Okay, so got my pen, blue. Let's go back here. So what do we know? Well, if I separate these two things out real quick, that might help us sort of visualize it a little bit better. Maybe I'll put this one down here. One thing that I know is I know that the diagonals are congruent. I mean, that's what we're going in with here. Okay. We also know that it's a parallelogram, and one property that we know about parallelograms is that opposite sides are also congruent, right? So I know that those two things are congruent. Now finally, I know that those two triangles share side CD, so clearly it must be congruent to itself, and therefore I can actually show that these two triangles are congruent by side angle side. Right? So let's get that down, right? It's kind of like almost a mini proof here, right? AC is congruent to BD, and that's really kind of given to us, right? Then we know that AD is congruent to BC, and that's because opposite sides of a parallelogram are congruent, and finally, CD is congruent to itself, and that's the reflexive property. And therefore, triangle ADC is congruent to triangle BCD by side, side, side. All right, so, if I'm told that I've got a parallelogram whose diagonals are congruent, then I can prove that, this triangle and this triangle are congruent by side, side, side. Okay. But, how does that tell me we've got a rectangle? Well, let's take a look at letter B. What can you say about angle ADC and angle BCD due to triangle ADC and BCD being congruent? Well, again, keep in mind that, let me label these. Here's ADC, and here's BCD. So I'm talking about this angle and this angle. What can I say about those two angles based on the fact that those two triangles are congruent? I can say they're congruent to each other, right? So angle ADC must be congruent to angle BCD by CPCTC, right? By CPCTC, right? Those two angles are congruent. All right, we're almost there. Letter C. How can we use B and the properties of angles in a parallelogram to conclude that both angle ADC and angle BCD are right angles? So how can we use that, right? Well, think about these two angles, right? And again, we're talking about this angle here and this angle here, and I can now actually mark them as congruent because we just proved that. Well, those two are adjacent angles of a parallelogram. And we know that adjacent angles in a parallelogram are supplementary, right? All right, so let's get that down, right? Angle ADC and angle BCD are adjacent, so are supplementary. All right, they're adjacent, so they're supplementary. All right, but we just proved that they were congruent. So if two congruent angles are supplementary, right, two angles that have the same measure add up to 180 degrees, then they both have to be 90 degrees. They both have to be right angles. All right, since they are also congruent, they both must be right angles. Now, Maybe we really should go on and also prove that angle DAB and angle CBA are right angles as well. But literally the argument we just made could have been made with those two triangles that are sort of on the top, if you will. Or at this point, you could also say opposite angles in a parallelogram are congruent. So if that's a right angle, that must be a right angle. And if that's a right angle, that must be a right angle. So at this point, because we've proved that these two angles are right angles, they must all be right angles. And therefore, gotta be a rectangle, right? Again, a remarkable fact. If I've got something that's a parallelogram, and that parallelogram has congruent diagonals, it's gotta be a rectangle. Sufficient condition number one. All right, let's play a little bit around with rectangles in the coordinate plane, because we want to do that. We want to do some of our geometry now in the Euclidean plane, which we just did, and some of it in the coordinate plane. Let's take a look at exercise number 5. Quadrilateral EFGH is shown below with vertices at E, -4, 2, F, 5, 8, G, 9, 2, and H, 0, -4. Letter A. Calculate the slopes of the four sides of EFGH. Explain how the slopes prove that EFGH is a rectangle. All right, so one of the things you may be asked to do, right, is given the 4 points of a quadrilateral in the coordinate plane, you might be asked then to prove that it's a rectangle. And the most straightforward way of doing that, in my opinion, is to prove that it's got 4 right angles. So we want to calculate the slopes of all 4 sides. Let's do side EF together and then have you do the rest of them on your own. So again, I'm not going to say EF equals because that would be the length of EF. I'm going to say EF with a little colon, okay, and that just allows me to then write something like this down. M is equal to, let's see, we've got 8 minus 2 over 5 minus -4. 8 minus 2 is 6, 5 minus -4 is 9, and I always want to simplify, and I'll get the slope of EF is 2/3. Awesome. What I'd like you to do now is pause the video and work your way around the figure. So then do the slope of FG, do the slope of GH, and then do the slope of HE or EH, however you want to look at it. Pause the video now and come up with the remaining 3 slopes. All right, let's do it. Here we go. FG. M is equal to 2 minus 8 all over 9 minus 5. That's going to be -6 over 4. Reduced, that's -3/2. Then I'll have GH. M is equal to -4 minus 2. All over 0 minus 9, that's going to be -6 over -9. That will reduce down to a positive 2/3. And finally, I will have HE. For HE, my slope is going to be 2 minus -4, all divided by -4 minus 0. That's going to be 6 over -4, which is -3/2. Now, a lot of students, after they've calculated these slopes, want to immediately jump and look at the slopes that are equal. Oh, 2/3 and 2/3. Those are equal, so EF is parallel to GH, and -3/2 and -3/2. Ah, FG is parallel to HG, all of which is true, but all of which really just goes on to show us that this is a parallelogram, right? But we already knew that because we knew that any kind of rectangle would be a parallelogram. That's not what we're trying to prove. What's more important is the fact that the 2/3 and the -3/2 are negative reciprocals, right? So we can now say EF is perpendicular, whoops, I don't know why I just did that. EF is perpendicular to FG, and FG is perpendicular to GH, and GH is perpendicular to HE, and HE is perpendicular to EF, right? Why can I say that all those things are true? Because slopes are negative reciprocals, and I can abbreviate negative reciprocals as neg recip, like that. And now I can say, therefore, EFGH is a rectangle because it has 4 right angles. That's great. And it's the most straightforward way of using coordinate geometry to prove that a figure is a rectangle. Simply calculate the 4 sides, show the 4 pairs of perpendicular sides. You don't want to just say EF is perpendicular to FG and GH is perpendicular to HE. That would only get you 2 right angles. And trust me, you can certainly have a quadrilateral that has 2 right angles that isn't a rectangle. If you don't believe me, here's a good example, right? Here's a figure that has 2 right angles that is not a rectangle. Side note, it is impossible to have a figure with 3 right angles that isn't a rectangle, but maybe you'll explore that a little bit more on the homework. All right. For right now, I just want to be straightforward. If I'm trying to prove it's a rectangle, 1 pair of sides that's perpendicular, that tells me that this is a right angle. The next pair being perpendicular tells me that's a right angle. Then the next pair, that's a right angle. And the final pair, that's a right angle. All right, but now let's play around a little bit more with EFGH. Let's take a look at letter B. Find the midpoints of each of the diagonals. How does this show that EFGH is a parallelogram independent of part A? So let's pretend now we didn't do part A. Let's pretend we don't know that this is a rectangle. What I'd like you to do is find the midpoints of both of the 2 diagonals, and if you want, draw the diagonals in first, but then use the midpoint formula to find the midpoint of EG and the midpoint of FH. And then ask yourself, why does that actually prove that EFGH is a parallelogram? Forget about the rectangle, just that it's a parallelogram. Pause the video now. All right, well, let's do it. Okay, for EG, all right, its midpoint, -4 plus 9 divided by 2, and 2 plus 2 divided by 2. -4 plus 9 is 5. 5 divided by 2 is 2.5. Yeah, that's right, I went decimal on you. And 2 plus 2 is 4 divided by 2 is 2. Okay, and FH, its midpoint is at 5 plus 0 divided by 2, and 8 plus -4 divided by 2. 5 divided by 2 is 2.5. 8 plus -4 is 4 divided by 2 is 2. And look at that. They have the same midpoint. And because they have the same midpoint, the diagonals bisect each other. And anytime a quadrilateral has diagonals that bisect each other, it is a parallelogram. All right, so since the diagonals bisect each other, EFGH is a parallelogram. When we did our lesson on sufficient conditions to prove something's a parallelogram, our sufficient condition set number 3 said that if the 2 diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. And again, it's really quite kind of cool. You know, this idea that if we find the midpoint of both diagonals, and this is the easiest way in the coordinate plane to prove a figure is a parallelogram. Calculate the midpoint or find the midpoint of both of the diagonals. If it's the same point, then you have a parallelogram, which is kind of cool. Now, let's take a look at letter C. Using coordinate geometry, show that the 2 diagonals have the same length. How does this, along with part B, show that EFGH is a rectangle? So now what I'm getting at here is that there's more than one way using coordinate geometry to prove that something is a rectangle. In letter A, in my opinion, we saw the most straightforward way, i.e. prove that it's got 4 right angles. But we can also prove it by sort of doing what we did in B and in combination with C. So what I want to do is I want to prove that the 2 diagonals have the same length, okay? And for that, we want to use the distance formula again. Now, that being said, Segment EG is a horizontal segment. See that, right? It's a horizontal segment because the two y coordinates are both 2. So I don't really need to use the distance formula to find the length of EG. The length of EG is 13 units long, which I could either figure out by counting the boxes or by taking the x-coordinate of G and subtracting the x-coordinate of E, right? So EG is simply 9 minus -4, which is 13 units long. All right. Now, if it were a slanted segment, I would definitely want to use the distance formula. But now let's figure out the length of FH. Okay, that one takes a little bit more work. So let's take a look. The length of FH, we're going to have 0 minus 5 squared plus -4 minus 8 squared. So FH is the square root of -5 squared plus -12 squared. -5 squared is 25, -12 squared is 144. And add those two together, we get the square root of 169, which is 13. So EG and FH are the same length. Now, how does that then combine with letter B prove that this is a rectangle? Well, letter B proved that EFGH was a parallelogram. Letter C proved that it was a parallelogram with equal length diagonals, and that was our first sufficient condition set to proving that something is a rectangle. So EFGH is a parallelogram with congruent diagonals so must be a rectangle. And that's another way in the coordinate plane of proving that a figure is a rectangle. You first prove it's a parallelogram, and you can do that actually in a variety of ways. You could prove that the diagonals bisect each other like we did, or you could prove that, the opposite sides are both parallel, which you could have done based on the slopes in part A. And then once you've proven it's a parallelogram, you could then show that the diagonals are the same length, and that then proves that it's a rectangle. All right, let's wrap this up. So the rectangle was the first of the special parallelograms that we really dug into, right? And the whole idea is that a rectangle is a four-sided figure with 4 right angles. Because of that, you can prove that it's a parallelogram, and all the things that go along with parallelograms then come along with rectangles. We also saw, though, that it was sufficient to simply prove that a parallelogram that has equal or congruent diagonals will be a rectangle. So that's one way of proving that something is a rectangle without having to show that it's got 4 right angles. On the homework, you're going to explore another few ways to see or to prove that something is a rectangle without having to prove it's got 4 right angles. But I'll let you do that on the homework. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.